Look at a pigeon. Really look at it. Notice the scales wrapping its feet. The way it snaps its head sideways. Sharp, precise scanning. The hollow bones you can almost see through its thin frame. That bird is a dinosaur. Not as a metaphor, not as a poetic comparison. Literally, genetically, biologically, that pigeon carries the DNA of the most dominant predators this planet has ever produced. The Tyrannosaurus rex lineage did not go extinct 66 million years ago. It shrank. It hollowed its own skeleton. It traded scales for feathers. And today, it raids your trash can and steals fries outside McDonald's. This is the story of the most radical physical transformation in the history of vertebrate life. And it happened so gradually that by the time the asteroid hit, the transformation was already halfway done. Here's a fact that sounds made up, but is completely verified by molecular science. A chicken is more closely related to a T-Rex than a T-Rex is to a Stegosaurus. In 2008, a team of paleontologists extracted preserved collagen protein from a 68 million year old T-Rex femur found in Montana. They sequenced it and ran a comparison against every living animal on Earth. The closest match was not a crocodile, not a lizard. It was the domestic chicken. So how does a 7-ton apex predator with 6-inch teeth become something you order with a side of fries? The answer starts 20 million years before the asteroid even arrived. And it starts with size. For tens of millions of years, a specific branch of theropod dinosaurs had already been trending smaller. Generation by generation, a few centimeters shorter, a few hundred grams lighter. These were the avian theropods. Feathered, fast, and increasingly bird-like, long before any of them could actually fly. When the asteroid struck 66 million years ago and blocked the sun for years, the massive dinosaurs were finished. Their enormous bodies demanded thousands of calories a day. With plant life collapsing and prey disappearing, they simply couldn't sustain themselves. But the small feathered theropods, they survived on insects, seeds, whatever scraps the dying ecosystem still offered. Their size, once a disadvantage in a world of giant predators, became their greatest asset. Smallness was survival, and survival, given enough time, becomes transformation. Now here is where the biology becomes genuinely astonishing. Take a T-Rex femur and cut it in half. It looks like rock. Dense, solid, heavy, built to anchor thousands of pounds of muscle and bone. Now look at a bird's femur under a microscope. It is hollow, reinforced by an internal lattice of tiny bony struts, structurally similar to the inside of an aircraft wing. Incredibly strong under load, almost weightless. This is called pneumatization, the systematic invasion of air sacs into bone tissue. And fossil records show it didn't appear suddenly. Early theropods show partially hollow vertebrae. Later ones show hollow limb bones, hollow shoulder bones, even hollow skulls. The skeleton was literally evacuating itself, generation by generation, making room for air. Then there's the wishbone, that V-shaped bone you snap at Thanksgiving. The furcula acts as a biological spring during flight, storing elastic energy at the top of the wing stroke and releasing it at the bottom. Scientists originally assumed it was exclusive to birds. Then they found it in velociraptors, in Allosaurus, in T-Rex itself. The wishbone was already present in theropods millions of years before flight existed. The structure was there. It just needed a new purpose. The tail tells the same story. The long, muscular, counterbalancing tail of the theropod, essential for bipedal movement on the ground, gradually shortened across evolutionary time, with the vertebrae fusing into a compact structure called the pygostyle. Today, that small bony nub at the base of a bird's spine anchors the tail feathers and functions as a precision aerial rudder. A predator's counterbalance became a pilot's control surface. every major structure in the body was repurposed, not replaced, repurposed, for an entirely different mode of existence. For most of the 20th century, the popular image of a dinosaur was gray, scaly, cold, and slow. That image is wrong on almost every level. In 1996, a fossil emerged from the Yixian Formation in northeastern China that permanently changed the field. Sinosauropteryx, a small theropod the size of a turkey, was preserved in such extraordinary volcanic ash that the outline of its soft tissue was visible. It was covered in fuzz, not scales, not feathers, simple hair-like filaments, protofeathers running across its body and down its tail. But the real breakthrough came in 2010 when scientists analyzed fossilized melanosomes inside those filaments. Melanosomes are the microscopic pigment-producing structures found in both feathers and human hair. By comparing their shape to melanosomes in modern bird feathers, researchers could determine color. Sinosauropteryx had a reddish-brown body with a boldly striped tail. Vivid, deliberate, almost ornamental, feathers evolved for display and insulation long before flight was even possible. Over millions of years, those simple filaments grew more complex, developing a central shaft, then branching barbs, then interlocking barbules that zip together into a smooth, unified vein. The asymmetric feather, where one side of the vein is wider than the other, is the specific structure that makes aerodynamic lift possible. Symmetric feathers trap heat. Asymmetric feathers catch air. The moment the first asymmetric feather appeared, flight became a question of time. Flight is the most metabolically expensive form of locomotion on Earth. A hummingbird beats its wings 80 times per second. Its heart runs at over 1,200 beats per minute during flight. Sustaining that requires a completely different internal engine than anything found in cold-blooded reptiles. Evidence from theropod bone structure suggests many of them were already mesothermic, running warmer and faster than modern reptiles, long before birds evolved. Rapid growth rings in fossilized bone point to high-energy juvenile development, a pattern seen in warm-blooded animals, not reptiles. But birds took this further with one of the most efficient respiratory systems ever evolved. Mammalian lungs, including ours, work like bellows. Air goes in, oxygen is exchanged. Stale air comes back out in the same way. It is effective, but it wastes a percentage of every breath. Birds solved this differently. A system of interconnected air sacs creates a unidirectional airflow through the lungs. Fresh oxygen moves through continuously, including during exhalation. There is no dead air, no wasted exchange. The result is extraordinary. Bar-headed geese migrate directly over the Himalayas at 29,000 feet, where the air is so thin that most mammals would lose consciousness without stopping. Their respiratory system keeps the oxygen moving regardless of altitude. This same engineering kept the avian lineage alive through the post-asteroid collapse, when the sky was choked with debris and temperatures swung violently. Efficient oxygen extraction kept their metabolism firing while larger animals shut down completely. The lung that powers a hummingbird through a rainforest is the same architecture that carried birds through the worst extinction in 250 million years. So where does the dinosaur end and the bird begin? Biologically, it doesn't. That boundary doesn't exist in the fossil record, and it doesn't exist in the taxonomy. Birds are dinosaurs, specifically the only surviving branch of the theropod clade. When scientists mapped the entire tree of vertebrate life, birds don't sit beside the dinosaurs. They sit inside the dinosaur family tree, nested within the theropods, as a living subgroup of a lineage that stretches back 230 million years. Archaeopteryx, the famous 150-million-year-old fossil with fully formed feathers, clawed wings, and a toothed beak, was long considered the definitive first bird. But we've since found feathered theropods older than Archaeopteryx that couldn't fly at all. The transition wasn't a single evolutionary leap. It was a long, continuous, overlapping spectrum with no clean dividing line. And the behavioral inheritance runs just as deep as the physical. Oviraptors, a theropod dinosaur, were discovered fossilized directly on top of their egg clutches, arms spread wide, in the exact brooding posture modern birds use today. The nesting instinct, the parental behavior, the territorial displays, all of it predates the wing by millions of years. Today, there are roughly 10,000 species of birds on Earth. They occupy every continent, every climate, every altitude from ocean surface to mountain summit. By raw numbers of species and global range, birds are among the most successful vertebrate groups in the entire history of this planet. The age of dinosaurs did not end 66 million years ago. It got lighter. It got faster. It repurposed every heavy structure in its body for something new. It survived the unsurvivable, adapted through the unimaginable, and kept going. The next time a bird lands near you, any bird, you're looking at an unbroken evolutionary line stretching back 230 million years. A predator that outlasted an asteroid, a skeleton that hollowed itself for the sky, a scale that over millions of generations became a feather. The dinosaurs are not gone. They are singing outside your window right now.